Hi everyone, and welcome to video number 7 of this series, in which we are learning how to model an end plate steel connection, which is this model that you see here. In the previous video, we have created the translators connected. So for example, here you have, let me select connector. We have created these translators that connect the beam to this coupling, and we applied a connector load to this translator to model the bolt pretension, right? We also have learned about the translator connector by using Abaqus user's guide. We know that we have this coordinate system with the x-axis connecting nodes A and B. We have only possibility of relative movement in the x1 direction, and we apply a connector load in this direction. So the software is going to move node A in this direction and node B in this direction, decreasing the distance between nodes A and B, and in that way it's going to end up applying the bolt pretension because the beam is connected here and there is a coupling connected here. So this node of the beam is going to be move in this direction, and this means that the beam is going to be, well, we are going to have a traction, a tensile load occurring in the beam, which is the representation of the bolt pretension. And this tensile load is going to be equal to the value that we have assigned here in the connector load. We defined it as minus 155 because of the way that we have defined the coordinate system. We have defined the coordinate system with the x1 axis from node A to B. And a positive load do the opposite. It tries to move node A to this direction, node B to this direction, which is not what we want. All right, so this is a summary of what we have learned in the previous lesson or video. Now let's continue working on this model. The next, and by the way, in the previous video, I have created only 3 of these connections, right? And I gave you as a task for you to create the other connectors. So in your model, you should have 8 connectors, okay? To do this, you just need to follow the procedure that I have shown. You need to create the connector, and then after that, you need to go to set list, modify content, and then include the new connectors. So that this set is going to contain 8 connectors in total. Okay, I'm going to press ESC because I don't want to modify anything. Close this. And okay, so before we start working on the contact, just to make sure that the layout of your ANSA is the same as mine, you should have these options activated here in the yellow buttons. Let's deactivate the visibility of points in the database and also curve. And let's select here Abaqus deck. And that's all. Now, to create a new contact, the first thing that we need to do, well, we have many ways to create a contact in Abaqus, many ways. And we have different kinds of contacts. We have node to surface, surface to surface, and etc. In this case, we are going to create a surface to surface contact. Guys, if you'd like to know more about contact, I have a blog article that I talk about it, that I have suggested previously already for my students. And there is also a pretty good video from Simulia that is about contact. I'm going to let the link to these 2 things in the description of this video. So let me just write it down here. So I'm going to contact blog article. I'm going to put the link to this in the description, and also the link to the Simulia tutorial about contact. Actually, in this article, I have this link there as well, but I'm going to also put in the description. It is a very good kind of tutorial. He explains about finite sliding, small sliding, node to surface, surface to surface. In the blog article, I also explain about it. So we are going to create a surface to surface contact. The first thing that I need to create is the set. I need to create one set with one surface and another set with another surface. Before we create the set, in the draw mode, this button here that controls the draw mode, let's select this option here, int. When we select this option, we are able to see the positive side of the faces or of the elements and the negative side of the elements. Yellow is negative and gray is positive. So for example, let me use the isolate tool, not. Let me select by feature angle and let me select this area here, mesomorph button and mesomorph button. I have these, which is the web of the beam, part of the web. And you see that one side is yellow and the other side is gray. So this is the positive side of the shell elements, and this is the negative side of the shell elements. One thing that we should guarantee is that there is uniformity in the orientation of the shell elements. So we cannot have something like this. Let's go to the classic topo module. And there is a tool that is very important here inside the faces group, this one, orient. If you don't find it, try to find it here in more options or search for it in here. Orient, left click and hold. And then we have these three options. For example, select this one, select. Activate the entity selection mode, zoom in here. Oh, in this case, I will not be able to select isolated elements because the mesh is assigned to this face. So I will not be able to show this actually. I would need to release the mesh from this face. I'm going to do this just to explain this. You don't need to follow what I'm going to do now. Just watch what I'm going to do because I'm going to undo this later. So the mesh is assigned to these faces. And that's why when I go to the classic topo module, I cannot see the mesh. I'm going to isolate this face. You don't need to do this right now, okay? And then I'm going to use a tool here named release. Release joint macro area boundaries while erasing mesh. Let me see one thing here. Okay, release, and then if I, oh, actually it's not this one. Let me go to the volume mesh, which is a module that we haven't seen yet. And then I have the release function here. And then this one, release shell or solid elements from the underlying geometry. Create a box selection, middlemost button. And now this mesh is not anymore connected to the underlying surface. If I go to the classic topo module and show all, you see that I can see the mesh here, but I cannot see the mesh on the other faces. So in the classic topo module, I can only see meshes that are not associated with a underlying face. Now, if I zoom in here, I'm going to isolate this. Oh, sorry, not the face. Actually, I'm going to hide the visibility of geometric entities. And to do this, I can deactivate this option here, geometry. And now I have only this mesh because this is the only mesh that is not associated to geometry. And then I'm going to zoom in here, classic topo module, and I'm going to use the orient tool, select, and then entity selection mode, and I can select one single element in this mesh. For example, this one. Middle mouse button, and then you see that the orientation of this element is going to change. Now the positive side is like this, while the neighboring elements has a different orientation. We cannot have this. Oh, this cannot happen. Okay. So what we can do is the orient tool has this option here, visible. If we select it, it's going to orient the elements in a way that all elements are oriented in the same direction. If I use again orient visible, it's going to change the orientation of all elements that are visible. Okay, so I can click here again, and it's going to change again. Anyways, I'm going to undo all these because I don't want to release this mesh. And to undo, instead of pressing Ctrl-Z many times, there is this tool here. We can click on this drop-down list, and there is a history of things that I have done. So I'm going to undo until the release function. I'm going to click on Show All. I'm going to activate visibility of geometry. And now we are back to this condition. What I'm going to do here, and now you should do this as well, in the classic topo module, orient tool, and there is this auto option, and then we have gray outside volume and yellow outside volume. This is when we have a closed volume. Faces defined a closed volume. But this also works in this situation where we don't have a closed volume. We can choose, for example, gray outside volume, and then the software is going to orient the faces in a way that it's going to look a little better. Okay? So this is something that I always do. It didn't change so much, actually. The thing here is that we're going to create a contact between the end plate and the column flange, right? We should look at the orientation of these faces. So you see that for the end plate, the side that we're going to have contact is this side here, right? Let me get here the face, double click on face, and then we have this face. We have all these faces that we are going to include in the contact. And the side of this face that is going to be in contact is the positive side, the gray side. And for the beam column, we're going to have the negative side in contact. Maybe in your model, you have something different. So you should look at your model, you see, and you should see what is the color of this face and what is the color of this face. Okay. All right, now let's go to the classic mesh module so that we see this mesh. And what I'm going to do now is to create a surface, two surfaces. To do this, we should go to the set list and right click and new. I'm going to create a surface by selecting elements. So I'm going to create a set of elements, and the software is going to use these elements to create a surface to be used in the contact. So first of all, we need to select in the database the filter that we want to use to select the entities for the set. I want to select shell elements. So select shell element here. And then to facilitate the selection, instead of having entity selection mode here, because, you know, in this way, I need to select one element by click. This is not effective. So what I'm going to do instead is to use the feature area tool, position the mouse here, and then you see that all elements in this area are going to be selected at once. Select this, and now you see that we have 436 elements selected so far. Select also these and these, rotate, holding the control button and left mouse button, and select this and this. You don't need to hold the control key to select more than one. You simply need to select with the left mouse button. You see that the orientation of all these faces is the same. Well, this should be the case, okay? And that's why we used the orient tool. Now we have, in my case, for 4,000 elements. In your case, probably this number is a little different. Middle mouse button to conclude. And let's give it a name. This is the end plate surface. Now, for this to become a surface, in the output as, we should select surface. And then in orientation, we should define the side of the surface that is going to be in contact. In this case, in my case, it is the positive side. You should check if in your case you have the same situation. So in here, I'm going to select as pos, which means positive, surface positive, and as neg is the negative side. And one very important thing, if you don't do this, it's not going to work. In the output type, you should select element. So translating, we are creating a surface by selecting elements. So in here we select element because we selected element. And then the orientation of this surface, and in here we need to say that this is a surface. And here we have the ID of this surface, and we are going to use it in the contact. You don't need to memorize it because we're going to open a list. Click on OK. And now we have this surface created. Now we should do the same thing, right click, new, shell selection mode, feature area, could be 40 degrees. Select this one, this one, this one, and this one. You'll see that we end up selecting more than we need. If you want to make your model more efficient, what you can do is to deselect these areas that we don't need. And to do this, left click in entity selection mode and use the right mouse button. Click and hold and create a box selection like this. And deselect until here, for example. Oh, sorry. I deselected too much. I'm going to select again. Okay. And again, entity selection mode. I'm going to get a view. And by the way, to choose a specific view, we can press F1, F2. In this case, it is F2. Right mouse button, and then deselect until here. And then right mouse button again, and deselect until here. Middle mouse button. And then surface. In this case, it's the negative side that is going to be in contact. Negative element. And then this is the column flange surface. Click on OK. And there we have it. Now we can close this and let's create the contact itself. So we should go to the Abaqus deck. Let me just drink water. So let's go to Abaqus deck and scroll down, and in the auxiliaries group there is this item here, contact. Left click and hold, and by the way, if you don't find it, again you can search it here, contact, and then it is this option here, contact pair contact. Okay, but I'm going to use this button, left click and hold, and then you see that we have this assistant, which is a tool that helps us create the contact. Sometimes I use it, but most of the time I follow this procedure that I'm showing. So I use the contact option, the first one. And then in here we can create a name for this contact. So this is the end plate to column flange. And then the type is contact pair. And then in here we have you see secondary and main. This is like slave and master, but it's not it's not politically correct to say slave and master, so they changed it to secondary and main. You see that we can select by element, node, surface, and etc. In these cases, even though we have created a surface, but we have done it by selecting elements. So we are going to actually select element here and not surface. And also here. And later in some future tutorial, you're going to see that we can also create a node to surface element, node to element contact. And then in this case, we would have to select node, but this is not the case now. So in this field, we need to select the set that we created that contains the slave surface. There are some rules that we should follow to select the slave and master. You can see these rules in my blog article about contact. In this case, it's not going to really matter. Okay, in this particular case, the element size is approximately, well, it's the same for both surfaces. The stiffness is the same as well. And this is a surface-to-surface contact. So we don't have that situation of, well, for example, in a node-to-surface contact, the nodes of the slave cannot penetrate the master surface. But in a surface-to-surface, this is not the case. We have the slave is not allowed to penetrate in the master, and the master is not allowed to penetrate in the slave. So anyways, for these reasons, because the mesh is approximately equal, the stiffness of the two surfaces is approximately equal. It's not so different. It's not like we are contacting a rubber with a steel part. And this is a surface to surface. Okay, I have just mentioned this. And what else? The size of the faces are approximately equal of the two surfaces. So for those reasons, it doesn't really matter. So let's select as slave. So select this field and question mark to open a list of sets. And then let's select the end plate surface here. Double click. And then in the master, question mark, and select the column flange surface. Okay. All right. So you see that we have so many fields here that we can talk about. Over time, we are going to learn more and more about all these options when we have the necessity to use some specific configuration here. What I'm going to teach you is the most general contact configuration, which is the one that I use most of the time. Just in some specific situations, more complex contact situations that we need to use some additional tools. Okay. So first of all, let's erase these two information. We are not going to extend the zone and smooth. You see that we have this small sliding field. We know that in a contact formulation, we have finite sliding and small sliding. In the Abaqus Users Guide, you can see more information about it, and also in my blog article. But an intuitive manner to think about it is that, first of all, this is a tracking algorithm. And Finite sliding is when we are going to have a considerable relative movement between the surface nodes and master nodes. When we have a lot of penetration, not penetration, but separation and contact with different areas and things like that. Small sliding is when we have just a small relative movement between the two surfaces. In this particular situation, that's the case. We are going to have a small relative movement. Okay. So we can choose here a small sliding, and when we do this, this is less computationally. This ends up bringing, I don't know how to say that. The computational cost is lesser when we choose a small sliding. Because then the tracking algorithm can work in a smaller area for each node in the slave surface to track contact in the master surface. Okay. So we can try to run it using small sliding. The model is going to run a little faster. But if we apply a too high load here and end up having too much sliding, then maybe we're going to face convergence issues. And then we should keep in mind that one thing that we can do is to put no here. Okay. All right. You see that we have this clearance option, which is to define the initial clearance between the two surfaces. Clearance is distance, initial distance between the two surfaces. In this case, since we have defined these two surfaces parallel to each other, and in a way that if we represent the thickness, we have zero distance between the two faces. Considering the thickness, I know that the distance without considering the thickness is equal to 20 in this case. But if we consider the thickness, the distance is equal to 0. But in here we can put it, for example, say yes and define 0 just to guarantee that the software is going to force this 0 distance. In this case, we don't need to do this. Okay, there is no need because this contact is perfect. But in some other cases, when the mesh is not so perfect, this can help. The type coefficients, we have node to surface and surface to surface. In this case, we have a surface to surface contact formulation. So the slave is not going to be allowed to penetrate in the master, and the master is not going to be allowed to penetrate in the slave. All right, so we have some other options here that are important, such as adjust. This one is really interesting, but we are not going to use this option in this tutorial. We need to do one additional thing here, which is to define an interaction. To define it, select this field, use the question mark, and then the software is going to open a list of interactions that we can choose. But we didn't create any interaction yet. So I need to right click here and new, and then I have just created an anonymous surface interaction. I'm going to rename it as surf interaction and plate column flange. To be honest, I don't always rename these things, but just for this initial model, let's have everything very organized. And then in here we can define many things related to the contact. What is going to matter is friction. But for example, you see that we can even define a surface behavior, and if we select yes here, we can select if we are going to allow separation. In this case, we need to allow separation. We are going to have some separation here in this region. methods, we can select the contact method. The standard option is penalty linear. Remember that we have stated about contact, right? In we have some material about contact in module 2 that we have learned about the penalty method, right? So remember that, let me see here. Remember that, yeah, this image is good. When we have two surfaces that are going to be in contact, initially, we can have a gap, and then we can think that in this gap we have many small springs here. But the stiffness of this spring is equal to 0 if this gap is greater than 0. And then we have this condition here that we have defined. Let me the Karush-Kuhn-Tucker conditions. If the gap is this distance here should be greater or equal to 0, which means that this gap here should be greater or equal to 0, and this is so that penetration is not going to occur. Because if the gap is lesser than 0, this means that we have penetration, which is this condition that you see in this image. Oh God. Anyways, we have studied this in details. You see in here we have penetration, and then this distance between these nodes is negative. And here we have this gap as a positive value. So the thing is that we have this restriction, but we know that in the penalty method, this restriction is not attended exactly, because we do have some penetration, and we are going to have some stiffness, normal stiffness in the contact. And when we have this penetration and we have a normal stiffness, we are going to end up having a force that is directly proportional to this stiffness and penetration. Okay, here we have the stiffness calculation. We know that this stiffness is calculated based on the penalty factor that we define. So I'm showing this to you because in this part, we can select here, for example, penalty linear, which is the standard option. So that's why I don't really define this, because it's defined automatically. And then in here, we can select a pressure over closure. By the way, you can see the definition of these things in my blog article. And then in here, we can define a specific stiffness for this contact. That is, we can define the stiffness of these springs that we have between the two surfaces. These springs that we have here. But I don't usually do this, because the software automatically calculates this stiffness based on the stiffness of the contacting surfaces. And usually, this automatically calculated stiffness is pretty good, and it generates a small penetration. Okay, I hardly need to, well, it's very rare to find a situation that I need to define a stiffness here. Because, well, if I see that there is too much penetration between the surfaces, then I'm going to force the software to have a larger stiffness here, and then we're going to have less penetration. You see that we have this scale factor also to define if we'd like to. This is also related to the stiffness. So let me go back to this expression that calculates stiffness, right? In the numerator, we have Fs. Fs is the penalty factor, which is this factor here. So the standard value is 1, but I can increase it to 2. So this is going to multiply the contact stiffness by 2, the standard contact stiffness by 2. So it's going to increase the stiffness. That's how I actually control the stiffness of the contact. I don't define a value for the stiffness. By the way, look at this description. if this field is left blank or is 0, the linear penalty stiffness has the default value. That is, the software is going to have a default value for this stiffness that is directly proportional to the stiffness of the contacting surfaces. So anyways, if I have a situation where there is too much penetration, I actually change the scale factor. So for example, I increase it to 1.1 or 1.2, I don't know. And then I run the analysis again and I check if the penetration is too large. And then I do this until the penetration is small enough. But I don't do this most of the time. One additional comment, this exercise is not really so much about contact. Okay, we can do later exercises that we need to work more on the contacts. But one important note here is that when we increase the stiffness of the contact, the convergence is harder. So when we have a larger stiffness, it's harder to converge the model. And when the stiffness is lesser, and it's easier to converge, but the penetration is going to be large. So there is a price that we pay when we want to decrease penetration, because penetration is an error. Because if there is contact between two parts, let me activate my camera. If there is contact between two bodies in the real world, there is no penetration between these two bodies, right? But in here, in the penalty method, there is some penetration, and this is an error. And if we don't want to have any penetration, we should insert here a very, very large value, an infinite value for the contact stiffness. But the model is not going to converge. So in here, we should have a good value so that we have small penetration, but the model converges. This software calculates this value for us. We don't need to do this most of the time. So select no here. And what matters in this tutorial is friction. So select yes here. And then we need to create a friction property. We don't have anything created, so I need to use question mark again. To open a list, there is nothing. Right click, new. And then this is a friction card. I'm going to name it as friction underline. And let's see how much friction we have. In this file, we have this information. Let me see where I have this information. I guess it's 0.44. Let me search for 0.44. Yep. So the coefficient of friction for the contact surface between the end plate and column flange was taken as 0.44. In this field, we have friction coefficient M, so type 0.44. And then in here we have all these options. For example, this one anisotropic is in case we want to have a different friction coefficient for different directions. In this case, in here we have an anisotropic condition, which means that this coefficient of friction is equal in all directions. All right, so that's all we need to define here. Sorry. Click on OK, and double click on this, and now we have that friction selected. Now we can click on OK, and now we have this surface interaction to use. Double click here, and then we have this selected here. So again, we have many windows. I know that at first you're probably getting lost, so practice. Go here and press F2 to open the interaction, and then we have this. And then inside here we have this friction, F2, and then we have this card for the friction. And so let's rename this as friction 0P44, so 0.44, just for organizational purposes. And then click on OK, and now we are back in the surface interaction. Click on OK, and now we are back in the contact definition. Guys, we are finished. The way that we have defined the contact here is the way that I define it 90% of the models that I run. Okay, just in some specific situations that I need to apply some other techniques here to help in the convergence. Now click on OK, and you see that in the database we have this new item, contact. Expand it, and we have a contact pair inside. Double click, and then select this item, and now we have the contact here that has been defined. The red surface is the slave surface, and the blue surface is the master surface, or the secondary surface, sorry, the primary surface. So we have the secondary surface and I guess it's like that, right? Secondary and main, not primary, main. So secondary and main. All right. So let's save this, and let me see. 41 minutes. We have 20 minutes yet in this class. The next thing that we can do here, we can set up the contact, the step that we have created in the previous class. Remember that when we created the connector load, the software automatically created one new step. And we can access this in this item, expand it. We have step and step manager. I'm going to talk about the step manager later. Let's go to this step. Select here, and then we have this step that we have named as bolt pretension. Double click here, and then we have this step card. Now we are going to use some FEA theory that we have learned in the courses, in the linear FEA course and in the non-linear FEA course. Okay, so first of all, here we have the name, the ID of the step, and the step manager that we have this step defined. We are going to talk about step manager shortly. We have this checked, which means that this is active. So this is important. We should have this active, because if we don't have it, if we don't have this active, when we output the .inp file, it's not going to be written in this file. Now we have all these options here, right? Let's talk about the ones that matters in this exercise. First of all, one very, very important is NLGeom. This means geometric non-linearity. We should say yes here, because I want to activate the solver that considers non-linearity because of large displacements and large deformations. Because we are going to have this condition in this exercise. So if we have this as no, the software is the software is not going to consider this. And for example, the calculation is not going to be correct because we do have large displacements and deformations. So we should have this as yes. And then the software is going to consider the geometric stiffness matrix of the elements, as we have learned in the theory part of this course. Okay, the next thing is unsymmetric. We learned in the linear FE course that the stiffness matrix is symmetric, right? But when we have a contact with friction that allows separation, and we know that this brings a nonlinearity, because this works like a new boundary condition in the middle of the analysis, as we have learned, right? In this material, we have learned why this brings a nonlinearity in the model. This ends up modifying the stiffness matrix of the elements when we have contact, because it's like this spring that represents the contact has 0 stiffness while this gap is greater or equal to 0, and then when this gap is equal to 0, then we have a new stiffness in the model, which is the contact stiffness, and this ends up modifying the stiffness of the whole structure. So that's why a contact brings a nonlinearity to the model. Now the thing is, when we have contact with friction, that is a non-linear contact, the stiffness matrix ends up not being symmetric anymore. The stiffness matrix of the whole assembly. And then the stiffness matrix becomes unsymmetric. And since we know this, because we know our model, we know that we are going to have a contact like this, we can already tell the software that yes, the stiffness matrix is going to be unsymmetric. And this is going to help the solver a little in the solution. Okay? So just memorize it. When we have non-linear contact, the stiffness matrix is going to be unsymmetric, and we should set this as yes. And by the way, if we don't do this, the solver is going to work normally. But when we set it as yes, we're going to help the solver a little, which is important. And notice that I'm using the term non-linear contact. I'm using this term because there are some contacts that doesn't bring nonlinearities, such as tie contact. That is the one that the surfaces are tied together. So we don't, it doesn't allow separation. It doesn't allow new areas to be in contact. In the beginning of the analysis, the areas that are in contact are going to be tied, and there is not going to be separation. There is not going to be new areas in contact. So this doesn't characterize a new boundary collision occurring in the middle of the analysis. So that's why a tie contact is not a non-linear contact. Okay, a non-linear contact is one that allows separation. So we can have separation in the middle of the analysis, and then we can have contact again, and this brings a nonlinearity. All right, now we understood this. Now we have this option here, solver. Let's remember that, let me show this. This is really important. Well, eventually, we are going to have something like this, right? The software calculates the stiffness matrix of each element, and it assembles the global stiffness matrix by using one of those two procedures that we have learned, right? And then we're going to have the global stiffness matrix, K uppercase letter, multiplied by the displacement column matrix that has all nodal displacements of the structure. And by the way, we are using a shell element S4 that has 6 degrees of freedom per node. So we have 6 possible displacements per node, 3 translational displacements and 3 rotational displacements. And imagine that this is per node. So if we multiply 6 by the number of nodes, we have the total number of degrees of freedom for the assembly, which is going to be the dimension of this column matrix, the number of rows of this column matrix. And this is equal to a column matrix that contains nodal forces, right? Now, the idea is that we know that we are interested in calculating the active displacements inside this column matrix. So we need to pass this to the other side. And then we need to inverse the stiffness matrix, multiplying by the inverse on both sides. Here we have the identity matrix, and etc. But the thing is, in reality, we don't inverse the stiffness matrix, because imagine that the stiffness matrix is very large, right, for a model like this. And to inverse a very large matrix is computationally heavy. So the software doesn't do that. Instead, the software uses a numerical procedure to solve this problem. This is a problem that involves a set of algebraic equations that we need to find the active displacement. We have studied all about it in details. So for my students, this idea is not abstract. They know what I'm talking about. We performed exercises we did with simple situations and extrapolated to more general situations. Anyways, and we have two methods. Actually, we have many methods, but what is used in Abaqus is the direct method, which is the standard option, direct method, that uses the LU decomposition method. We have learned how to use it, right? It's simple, and this is the direct method. But we have also another method, which is the iterative method. The iterative method uses an iterative procedure to find the active displacements by having this set of algebraic equations defined by this matrix equation here. Right? Remember that the iterative method, and then if we go back here, the solver option has iterative. And then if we don't choose iterative, then the LU decomposition method is going to be used. Guys, 99% of the time, I use the standard option, the LU decomposition method. Okay, 99% of the time. And if the module is very, very large, like really large, this is not a large module, guys. A large module is one that has like 5 million elements. This one here has 136,000 elements. Then maybe it's worth it to use the iterative solver to solve this set of algebraic equations and find the active displacements. Just one last note. Remember that even though this is a numerical procedure that we use instead of inverting the stiffness matrix, the solution is exact. It doesn't mean that it's going to solve the mathematical module exactly. It just means that this method is going to solve this set of algebraic equations exactly. But in this calculation, we know that we have errors introduced because this is a numerical procedure. Okay, but at least this solves this set exactly. But it doesn't mean that the exact solution of this set of equations is going to bring the exact solution of the mathematical model. That's my point. So we don't need to do anything here. In this subheading, we can just insert a description. So this is a step used to apply bold pretension. We can put any type of description here. Analysis type. Just 1 second, guys. Analysis type. Here we are going to select the solver. In here you have selected static. So this is a static solver. Well, this is very important because in here we are defining part of the governing equations defined in the domain of the analysis. So this is the domain, this geometry here that we have discretized using elements, finite elements, right? And let's remember that, let me open up a material here that is part of the linear FEA course, the equations of elasticity module number 6. And then here at the end, we have the governing equations for a three-dimensional problem, which is our case, right? So you see that we have the stress-strain relations, we have the strain displacement relations, and the equilibrium equations. So when we choose a solver here as static, we are telling the software, use these three equations, the equilibrium equations, as the governing equations. Okay, it's really important to have these in mind, to have complete control of what is happening behind the software. Okay, so when we choose it, we are telling the software that f equals ma, but a is equal to 0, and translating this for a three-dimensional situation, we have these three differential equations that we have obtained using Taylor series. We have learned in details this in here. Okay, it's actually simple. I know that it looks complicated because these are differential equations, but this is pretty simple to obtain these expressions. We use Taylor series with the two first terms, and anyways, I explained this in details. But in here we have other kinds of solvers as well. You see, I have the buckle that performs linear buckling analysis. Maybe we can perform an exercise like this. In the course, we have performed exercises using the linear buckling solver, but we can perform some more complex analysis, such as recently I have performed one of a water tank, a very large water tank, and I needed to calculate the buckling load using the linear buckling solver, and then I needed to also calculate buckling using a nonlinear solver by using the results of this one. It's a pretty interesting procedure. If you'd like to, I can show to you. Anyways, we have many solvers here. We have the dynamic explicit solver. We have even a CFD solver. Frequencies for module analysis. And anyways, in this case, we're going to choose static so that we are defining these three differential equations in the mathematical module. All right, the last thing that I'm going to show here in this video is parameters. In parameters, and by the way, you see that we have these risks methods. This is related to the nonlinear buckling analysis. But let's set this to no. We're not going to use the risks solver. This is very interesting because we have learned about the Newton-Raphson method. By the way, I have a blog article that I teach how this works, the Newton-Raphson method. I'm going to let the link in the description of this video. Newton-Raphson blog article. I'm going to put it in the description of this video for you to check out. We know that the Newton-Raphson method is the one that is used to update the stiffness matrix inside each increment that we have in the nonlinear analysis, right? We have iterations of equilibrium inside one specific increment, and for each iteration of equilibrium, we need to update the stiffness matrix. Actually, the Newton-Raphson method is used to check if the model has converged or not. So it calculates the residual forces and moments, and if this is above a limit that we define or the software defines, then it's going to perform one additional iteration of equilibrium. So the stiffness needs to be updated. This is something that we have learned in details. The risks method uses another kind of it's not the Newton-Raphson method. It uses the arc length method, which is one that allows a negative stiffness. But anyways, we're not going to talk about it in details in this video. So we should have this as no. We are going to use the Newton-Raphson method. And this is stabilizer. Nothing here matters. What matters is these fields here. In this field here, we define the total pseudo-time. Remember that in a static analysis, time does not have a physical meaning. It works like a percentage of load. So if we define here as 1, this means that this is the total load that we are going to have applied. This works as 100%. So this is the total load that we are going to apply. And this is the initial load that we are going to apply, the time increment. So if I define here as 0.1, this means that out of 1, I'm going to start applying 0.1, which means 10%. I can even define this as 110. So this is 10 out of 100, which means 10%. Usually, I like to define it as 1 and 0.1. So, in the first increments of this nonlinear finite element analysis, we are going to start applying 10% of load. Or if we define the boundary condition as a displacement, and then the first increment is going to be 10% of this displacement. If I define here as, I don't know, 0.2, in the first increment, we're going to start with 20%, and so on. So the thing is, we can define the first increment, and then the next increments are going to be defined by the software, as we have learned in the theory. Okay, usually I like to define it as 10%. Here we define the minimum increment that is going to be allowed. Usually I don't really define it, but when I define it as 1e minus 9, which is a very small value. So if the software needs to define an increment lesser than this, then the analysis is going to be aborted. The software is going to stop working, and then we need to fix some issues that we might have. And this is the maximum increment that we can have. Sometimes this is important to define, for example, when we want to extract a curve from the model, it's important to not allow the software to take too big steps or to define too large increments if the analysis is easy to converge, because then we are going to have less points to create the curves. In this case, we will need to create some curves. So I'm going to allow 20% as a maximum increment. Okay, and we can click on OK, and that's all we need. In the next video, we're going to yet define the output requests, but I need more time to explain about it. So we're going to do this in the next video. Okay, now click on OK, and File and Save. And that's all I had in this class. I see you in the next video.